Hello everyone, I'm going to be talking about movement artifact robust mental workload assessment during physical activity using multi-sensor fusion. So this work is with the help of the folks at the University of Laval and Thales. So in general, mental workload constitutes one of the three psychological states which make up operator functional state. This is something which is quite critical in understanding job performance. Now, most of the studies that have uh, been done to understand mental workload and if we can predict it have been done in a laboratory controlled environment with the use of a lot of biosignals such as ECG, EEG, etc. But now with wearable devices and the reality of what jobs are like, which actually involve a lot of moving around and motion, it's possible to monitor these ambulatory jobs and like at least emulate conditions which are more real and in the wild. However, doing so will involve its own challenges. There's more movement noise in the data, and on top of that, there is a change biosignal dynamics. A person's heart rate could be elevated because they're running or they're just stressed. So, how do we distinguish that? Uh, some of the good examples of ambulatory jobs are first responders, police, and firefighters. Both of these jobs are quite critical. Any kind of fatigue or inability to make decisions can lead to very dangerous situations for everybody. So monitoring workload in such jobs is quite key if they need to be done properly. So just a small note on the importance of different kind of sensors. So there are three main systems that we have. The central nervous system, directly signals coming from the brain, the parasympathetic and sympathetic systems. Now, all of these systems respond differently in different organs, and this is something which becomes key when trying to use sensor fusion, because that can give us complementary information, leading to improved prediction. Uh, One other advantage of this is these sensors, they are the signal streams, they are independent of one another. So heart rate and breathing, even though they might be measured from the same sensor, they are coming from different kind of equipment. So if one might be not working because of, let's say, electrode movement, the ECG goes off, the other still might be useful. So we might still get the usefulness of breathing, which is recorded in a different way. So a little bit about the experiment that we conducted. So the idea was always to kind of mimic ambulatory jobs. That was done using two different physical activity types, which was 21 subjects on the treadmill and 27 on the bike. Um, and there were three physical activity conditions involved of no, medium, and high, corresponding to stationary, both on the bike and the treadmill, and then slow and fast biking, and walking and running on the treadmill. So in order to look at mental workload, we use the MADB2 software, which is quite well known for mental workload studies. It basically is a flight emulator, which has several different tasks. One would be this aiming task where you have to kind of make sure that the cursor is in between this small box. One is with pumps where you have to manage the levels of both of the pumps. And the third one is the bars, where you have to make sure that the bars are in a specific range. So you're doing monitoring multiple things at the same time. And the mental workload level of this task can be manipulated to high and low mental workload. So we collected data from a bunch of devices. With the Enobio headset, we got EEG from 8-channel electrode, mostly from the frontal, because that has been well known to be of significance when studying mental workload. We also collected blood volume, pulse, skin temperature data, and GSR from Empathica, and ECG and respiration from BH3. For the protocol, the experiment consisted of 6 sessions, which is three physical activity states and 2 mental workload states, which were randomized. Each session had two baselines of eye closed and eye open, with no physical workload in one and physical workload in another, and also subjective evaluation at the end, which was subjective evaluation of mental workload at the end, which was done through NASA TLX questionnaire. This is what the experimental setup kind of looks like. One on the left, you can see the treadmill condition. Sorry, the bike condition. On the right, the treadmill with a harness attached at the back, just to ensure participant safety. So there are a lot of different signals, and they need to be processed in one way or another first to get get a clean signal from which we can extract several significant features. It varies from signal to signal type. For a lot of them, it might be bandpass filters of different ranges. And for some, it might be a little more complicated. For example, for EEG, we use the wavelet ICA. There might be additional processing involved as well. For example, for ECG, we finally extract the QRS complex and the RR series. For EEG, we do the band decomposition into these specific bands. And then for GSR signal, we extract the phasic component, which is related to arousal and can indicate mental workload levels. The features extracted were quite simplistic. They were basically the benchmark features that are well known for a given modality. So for EEG, the spectral band features, spectral band power features for all the different subbands. For interbeat intervals, the RR series, the time and frequency domain heart rate variability features. And for others, it was a pair of spectral and descriptive features. In the descriptive features, there were just statistics, while in the spectral features, they consisted of spectral band energy over specific bands, as well as spectral ratios, peak and centroid for the breathing signal. These features were extracted over a 60-second window and a 45-second overlap for each 10-minute session. Finally, for evaluation, the feature sets considered were basically features extracted for a given sensor. So an OBO bioharness in E4. The evaluation was done separately for activity types. So bike and treadmill had a separate evaluation and different levels of no, medium, and high. Balanced accuracy was used as a metric of evaluation with a leave one subject out setting. We used quite a simple classifier here, a logistic regression, and then use the classifier weights to understand the feature importance in the decision-making process. So there can be two specific sources of noise which can corrupt the data that we are collecting. One is related to the signal artifact, which are usually short duration fluctuations in the signal, while others can be attributed to the subject. The subject might be distracted. So what we might be recording is not really mental workload, but just some random activity, mental activity. So for a 10-minute session, like taking several of these 60-second epochs, they might be corrupted by both of these sources. A way to get around that is making a session-wise decision based on majority voting of the epochs considered within a session. The one advantage of this is it gives robustness to the noise mentioned above, but a big disadvantage is that we are losing time resolution in results. If it's a 10-minute session and we are making a decision, so we get one decision after every 10 minutes. So the real time advantages kind of get decreased. So the results you can see for different physical activity types, features, feature combinations, balance accuracy for each epoch, and balance accuracy per session. So for the treadmill, the combination of all the sensors gives the best session-wise accuracy for all the three cases. While all sensor fusion is great for no and high physical workload, an OBO, which is the EEG signal, performs the best in medium, which actually gives this importance of EEG for physical activity, mental workload assessment. Now for bike results, the story is a little different. The results are not as high as treadmill, and they don't even beat the random voting in a lot of cases. Medium physical activity gives the better performance than random voting, and it's the only case where we observe such a thing, which is interesting because it does not include the NOBO at all. It's using the Empatica and BH3 feature sensor combination. Some of the possible reasons for this could be inherently there's more mental demand when a person is doing the task on a treadmill, because along with movement, there'll be quite a significant head movement, and focusing on a screen becomes harder. And this was something that was observed and reported by the participants themselves. Another could be distraction from the seating position. Some of the participants did report that the seat was a little uncomfortable, and this could have caused a lot of distraction during task, hence leading to a bad performance. Finally, to conclude, multimodal fusion did help to improve robustness, and there was a lot of differences observed in mental workload performance due to physical activity in bike versus treadmill case. Session-wise analysis can further improve noise robustness, but at the cost of losing time resolution. And finally, EEG is an important modality for overall performance improvement, at least as observed for the treadmill case. Something important to note here is that the database and a paper describing the database is now available in Frontiers, and you can access it through the QR code. You can also access the signal pre-processing and feature extraction codes used in this study. If you have any questions, feel free to reach out at my email, and thank you very much. You can always connect with me on Twitter and LinkedIn. Thank you so much.